Test, test, test. Okay, good evening. Let's get started. Thank you. Let's continue on the spherical coordinates for triple integral. Okay. Here's a quick review of what spherical coordinates are. So this is what we have done at the end of the previous lecture. Spherical coordinates refer to three brand new coordinate variables, rho, phi, theta. And rho, phi, theta are defined, okay, in the reference frame XYZ reference frame. Rho is the distance from origin to where the location point P is, and phi is the angle from the z-axis to where this OP is. Okay. And then theta is the angle from x-axis to where the projection of the OP in the XY plane. So theta is basically similar meaning as the polar coordinates or the cylindrical coordinates theta. Okay. So that's your rho, phi, theta. Now precisely, rho, as we said, is the distance from origin to point P. So if point P has coordinates x, y, z, then the rho is related to the x, y, z as simply just a square root, x squared plus y squared and the plus z squared, right? So rho itself is a natural number, it's a number naturally more than 0 or greater than 0 or equal to 0. Okay. The phi here, as you can see, is the angle between the z-axis and OP. Okay, so this is your z-axis, this is your OP. We actually has a range of phi here is 0 to 2 to pi. So basically, if OP align up with the z-axis, then 0 degree, and when it's at the bottom here, right, that's pi degree. So your phi angle should not be more than pi and should not be less than 0. Okay. We'll see that. Okay, so this is your range of the pi here. So if you later try to find the limits for the pi, okay, if you somehow wrote down the limits, for example, pi equal to let's say 5 pi over 2, for example, so more than pi. Okay, so then it's actually not right because you know your maximum range for the phi is pi. Okay, so that's something that you keep in your mind. Okay. And of course, the theta can be certainly between 0 and 2 pi. So this is a definition of spherical coordinates. So essentially, if I make a little bit of analogy, as we did in previous case here, you can consider at this location, you have a coordinate system attached to this. There's a unit x, unit vector, okay, attached to, let's call this E rho. Okay. So in the direction of the rho or OP direction, right? So that's a unit vector in that direction. And then you have another unit vector in pointing to the theta direction. So that will be E theta in that direction. Okay. And then there's another unit vector pointing in the rotation of the phi angle direction. So that will be in this direction, E phi. Okay. So that three unit vector together will give you a coordinate system, which basically represents this as a spherical coordinate system. All right. One of the usage of spherical coordinates it's very useful is, especially if you're a civil engineer or study also geology, the reference to basically the Earth. Okay. So if this is the Earth, you set up your XY coordinate system for Earth, this X axis at here. Okay. So typically, right, passing through this is basically the equator. Right. So this circle here represents an equator, the equator, and this circle here, okay, is the so-called prime meridian. Right. It's a circle passing through somewhere in the British domain. Okay. Oh. Right, Greenwich time, that's basically that circle is. And then you set up your x-axis going through this, okay? Yeah, so going this direction is east, and then going that direction is west, right? And the z-axis, sometimes we call it the zenith. Right, so that's your z-axis, okay? And then any circle, okay, any circle that's parallel to the equator, right, is called the latitude, right? Certain latitude circle. Okay, any other circle, you know, and then going downwards, okay, is called the longitudinal circle or line. Okay, so if you have a, let's say you pick a point here, you draw an angle here. Okay, so then this is your theta, and this is your phi, and that's your rho over there, right? According to the definition of the spherical coordinates that we have defined at here. Okay, so the phi angle at here, basically in terms of this notation, is how much angle from the zenith, which is the z-axis. Okay? And the theta angle would be how much angle is it, right, from the x-axis. But the x-axis is the, so theta here, okay, there's a name for it, is called azimuth. Okay. It's called azimuth angle here. And the phi here, there's also a name called the zenith angle. So that's from the Earth's perspective, right? How the spherical coordinates is related to it. And rho, of course, is the radial distance from origin, right, to the point. So wherever the point is on the surface of Earth. Okay. So you can use the three variables to actually decide on the actual location, right, of this point P. But of course, we always consider Earth as a constant radius. So the rho is a constant. So literally you could just use theta and phi, which often in time we just say what's the latitude, what's the longitudinal, right, to decide on the actual location. Okay. Okay. So let's say what we can do, okay, in terms of the spherical coordinates to calculate this triple integral for our purpose. Now, before we start actually looking at the triple integral problem, let's get ourselves familiarized with spherical coordinates and its relationship with Cartesian coordinates. And let's refer back to this diagram at here. Okay, so let's find the connection between Cartesian and spherical coordinates. As you can see labeled here, X, Y, Z. Okay, so Z is right here, and that's your Cartesian coordinates. And then you have your rho phi theta. Okay. So first of all, if you look at this triangle here, and it's the right triangle, okay? So you can see this, if this is phi, let me erase this three things in here. And then this is phi, right? Yeah. So now you can actually start to calculate relationships between spherical and Cartesian. So if this is Z at here, so technically you can see the Z, right, equal to rho. If this is rho, this is phi, rho times cosine phi to give you the Z. right? That's from this triangle at here, okay? And x is over here, y is over here. As you can see, your x, right, equal to this r times cosine theta. And what is r then, right? R, you can get it from this triangle over here, which is rho times sine phi. So rho times sine phi cosine theta. That's your r. And similarly, your y is r sine theta, and that gives you rho sine phi sine theta. So this is your fundamental connection between Cartesian and spherical coordinates. So we need to, if we need to use spherical coordinates, okay, based on the given Cartesian coordinates expression, then I need this expression right here to help me convert everything into the spherical coordinates. So let's take a look at the example together, right? So let's say I have a Cartesian expression. X squared plus y squared, and then plus z minus 1 squared equal to 1. So this is a very common equation. I think you probably know what it is. This is essentially, it's a sphere with a center at 0, 0, 1. And its radius is 1. Right? So if you're required to sketch this sphere, then you can find its origin first, find its center first, which is 0, 0, 1. So that's your x, y, z at 1 here. And then radius is also 1. So then you can start to sketch a sphere with center over there. Okay. Okay, that will be your the sphere, what it looks like in x, y, z coordinates. Okay. Yeah. Okay, so now the question is, what would be a spherical coordinate expression for the same sphere, right? So this is what we're going to find out. Let's substitute the expression for x, y, z into the left side of this spherical surface here. Okay. I substitute x with rho sine phi cosine theta, y with rho sine phi sine theta, and z with rho cosine phi. It's a little bit long expression, but many things can be simplified. Okay. That's your x squared. That's your y squared. And this is the z minus 1 to the power 2 equal to 1. Okay. And then let's look at the first two terms. Okay, the first two terms you have, sorry, did I write it wrong here? So this is sine. This is sine here. Yeah. So the first two terms you have a common factor. Rho square sine phi square. This is a common factor. So you take out the common factor, you're left with cosine theta square plus sine theta square, which is 1. So these two terms will be simplified to rho square sine phi square. Okay, that's your first two terms simplified to this. This term here, let's expand it, right? Expand because this is rho cosine phi minus 1 to the power 1 to the power 2. So let's expand it. So rho square cosine phi square minus 2 rho cosine phi plus 1 equal to 1. Okay. So expand that bracket and you get this expression. And then clearly you can see the first two terms has a common factor rho square. So you take out the common factor rho square, and you're left with sine phi square plus cosine phi square again, which is 1. So you basically get a rho square and minus 2 rho cosine phi. And this one and that one cancel each other. So this whole thing equal to 0. And then you got a common factor rho for these two terms. So take out the rho here. So rho minus 2 cosine phi equal to 0. Okay, so this is the simplest that you can get. And then based on this expression, right, you have a left side equal to the right side, which is 0. Then the only way to make it a 0 is either rho is 0 or rho equal to 2 cosine phi. Right? And only these two conditions will make that right side to be 0. Now, you certainly don't think this one should be kept, because how could rho be 0? Because you have a surface, you pick any surface, rho is not 0, right? So your only solution here is this, which is rho equal to 2 cosine phi. So this is equivalent expression in spherical coordinates to describe the sphere over here, which is a circle centered around a 0, 0, 1 with a radius of 1. Okay. You actually really need this kind of expression to help you in terms of finding limits. Okay, but there's an alternative way to get this expression too. Okay, so I'll show you another way to get this expression. So here's a sphere, right? Starting from the Cartesian coordinate from the drawing. Now I'm going to create a big circle. So anywhere is fine. You know, big circle. Just create a circle across this globe. And then you can pick any point on that circle. Okay. Then you can form a triangle from here, connect the top peak to the point on the surface, and then to the point of the origin. So basically, I create a triangle here, and that triangle is part of that so-called great circle. Essentially, when you slice a globe, right, you will get a circle as long as the slice is going through the diameters over here. Right? So if I look at the flat here, I get, this is what it looks like, right? So that's the circle that I have just created. Okay. And this is the point on the surface of the sphere. So according to the definition of the spherical coordinates, if you look at this line here, right? This is the line from origin to the point where we picked, then the angle from the z-axis to this line, right, which is basically this angle here, is the definition of the phi, right? It's the phi angle. Okay. So that's your phi angle over here. Right? And then from here to here, and that's the rho, right? That's from origin to the location of the point, and this is the rho at here. Now from here to here, and that's the distance, which is the diameter. In this case, 2. Okay, so now you can see for, of course, the other fact is, and this circle, this triangle here will be a right triangle. Okay, this is a geometrical property. So if you create a triangle based on a circle, with hypotenuse here is passing to one side is basically diameter, and one side has a point on the circle, then it's guaranteed this is a right triangle. So you look at this right triangle here, you can easily create a relationship. You can see what rho equal to 2 times cosine phi. Okay, and that's the same result as we have obtained over here. Okay, so there sometimes consider it a little trickier situation is to find the rho limit, right, through this certain region, and you probably have to find the rho limit using this sort of a geometric relationship, or you can use the results like this. Okay, so that is the connection between the spherical coordinates and Cartesian coordinates. There's another example I can show you, which we actually already showed previously, okay, is the cone example. Okay. For example, right, this is the expression for the surface, and we have already demonstrated in the previous lecture. We said this is a cone, right? All right, so let's further verify this using spherical coordinates. Okay, spherical coordinates. So first of all, you know, if you pick any point, okay, on the top edge, you create a line, radial line, okay, through the surface of the cone, and then according to the definition of spherical coordinates, then from the z-axis to that line, then that's your phi angle. Okay. So we actually demonstrated before that phi will be pi over 4. So let's demonstrate again. Let's see if we actually get a phi equal to 4 here. So what we're going to do is we have the relationship XYZ and our rho phi theta. So I'm going to replace the expressions over here. So Z is rho cosine phi. So I'm going to replace Z with rho cosine phi. And then X is rho sine phi cosine theta squared. And then rho sine phi sine theta squared. Right, that's your X and a Y. Okay. Again, you got a common factor rho square sine phi, so you end up with just a rho square sine phi at here. Okay. So rho is a positive quantity. And sine phi, what about sine phi here, right? So remember, phi angle is between 0 and pi. Phi is always between 0 and pi. So if a phi is between 0 and pi, that actually makes the sine phi to be a positive number, right? Sine angle, you remember sine looks like this. So this is 0, this is pi. So between 0 and pi, sine is a positive number. So then this square root becomes rho sine phi. So basically rho cosine phi equal to rho sine phi. And then you cancel rho, you got a cosine phi equal to sine phi, which is tan phi equal to 1. So phi equal to pi over 4. That's the same results as we have derived when we talk about using cylindrical coordinates, if you recall that. So basically, this cone surface, okay, you can express it using cylindrical coordinates. If you recall that in cylindrical, what is that? Z equal to R, right? In cylindrical. And you can also express that using spherical, which is phi equal to pi over 4, okay, for this surface. Now, similarly, if you recall, we also demonstrated if I plug in a coefficients in front of the square root term, then the geometry of the cone will actually change. Right? Either it becomes lame or become a wider cone. Okay. You can certainly use exactly the same approach that we have it over here. You can demonstrate. You'll see that in this case, phi equal to pi over 3. Right? So that will give you this exactly same results. Okay, so sometimes there are some surface, as I can show you here, much better to be expressed by spherical coordinates. So as you can see, this one here is called a wrinkle sphere. Right? It will be much harder to express that using Cartesian coordinates. But you look at the expression using spherical is very simple, right? So like giving you an orange at here. And if you vary the numbers at here, you actually get a very wrinkled sphere. Okay. So That's how sometimes surfaces, right, are better expressed not using Cartesian coordinates, but using some other different coordinates. Same thing for in terms of in planar case, right, using polar instead of using Cartesian. All right, so let's get back to the triple integral, right? Okay, so triple integral, the idea is we want to calculate triple integral using spherical coordinates. This is your original spherical coordinate. This is the original Cartesian coordinates triple integral, but I'm not going to do that in Cartesian anymore. So we wanted to calculate everything using spherical. So what do we do? The x, y, z, we have to replace that x with rho sine phi, and then cosine theta, and y with rho sine phi sine theta, and z is rho cosine phi, and dv, right? dv is not going to be dx, dy, dz anymore. So it should be something like d rho, d phi, d theta, right? These three new variables. So the question is, okay, what should be insert over here, right? It's a certain scale factor at here. So this is where, if you recall, this question mark, right, should be given by the determinant of the Jacobian matrix. Basically, it's like a transformation of a coordinate system. Instead of using x, y, z, you're using rho phi theta, right? So without going to that detail, I mean, your transformation matrix for J should be, the Jacobian matrix should be calculated as partial x, partial rho, partial x, partial phi, partial x, partial theta. Same thing, partial y, partial rho, partial y, partial theta. And the last row is partial rho, partial z, partial rho, partial z, partial phi. Okay. That's what the Jacobian matrix is. You calculate 9 partial derivatives based on the expression of x, y, z given as these are given here, and you plug it into this 3×3 matrix. Then you calculate the determinant of this 3×3 matrix, and you end up with rho square sine phi. Okay, rho square sine phi. Again, because phi's range is between 0 and pi, so sine phi is naturally more than 0. So technically, this should be a determinant of the Jacobian, absolute value of it. Okay, but because all the numbers here are naturally positive, then you don't need an absolute sign anymore. Okay. Okay, so the question mark basically should be replaced with rho square sine phi. Okay, so that's what I'm going to replace over here. So this is going to be rho square sine phi. So in terms of formula, if you want to remember formula, then your triple integral in terms of a spherical coordinates should be this. So don't forget rho square sine phi. All right, if in polar we have r, in cylindrical we also have r. Over here we have a rho square sine phi. That's a little bit different. Yeah. And then d rho, d phi, d theta. Okay, so the next question basically is we need to find the limits for rho, for phi, and theta, so then we can calculate this triple integral, right? Okay, so that's what we're going to do. We'll see how we can find the limits for rho, phi, theta, using the same approach that we have done previously to scan through this region and find the limits for each one of the variables here. I'm going to demonstrate using an example, okay, to show you how we find the limits for rho, phi, theta. Okay, so first of all, let's consider that we have a region given by two surfaces. One surface is x squared plus y squared equal to 1. And the other surface is z equal to 1 over root 3 square root x squared plus y squared. And then calculate the volume of this region D. So basically, the integrand F is 1. Okay, so just calculate the volume at here. Step 1, I need you to be able to sketch the region D for some of the very common type of surfaces, okay, bounding this region D. You should be able to sketch that. Although most of the time you probably will be given a sketch, but I think as a basic skill, you should try to sketch this region D. All right, in this case, okay, so let's look at the region D. It's bounded by these two surfaces. The first surface, it's a sphere, right? And the second surface, we have just done that. It's a cone. Okay, so let's draw the cone first. And we know the cone is somehow the angle phi there, as we just did, is was pi over 3, 60 degrees. So just draw it roughly like that. Okay. And then this is a sphere with a radius of 1 and centered around the origin. So basically, in your head, you should try to visualize, okay, so there must be right on top of this cone is that spherical surface, right? So the spherical surface is on top of the cone. And then what's between is the region D. Okay. Now this time is really look like an ice cream cone here, right? You have on top of this cone here, you have certain ice creams. So that's what this region looks like. Okay, a better computer drawing will show you something like that. Okay, and we're looking for the volume of this region D. Good. Okay, that's your first step. Sketch region D. Okay, and the second step, for this, under the first step here. Okay, you need to also draw the shadow R of the region D, okay, in XY plane. So the nature essentially is sort of a determined here, as we're going to show you. The order of the integration, again, most of the time, you probably will follow the order d rho, d phi, d theta, okay, like what I wrote at here. It doesn't mean that you cannot follow different order, but this order proved to be the most convenient way to conduct calculations under spherical coordinates. Okay, so that will be the second step. Okay, is under the first step is to draw the shadow of the R, okay, in region D, because you need the R to determine the theta limits. Okay, so in this case, you project this whole region D into the XY plane, which is the shadow. So that certainly give you a circle. Okay. You actually don't need to write down the equation in the circle. Okay. As long as you know this is a full circle here, that's fine, because that's all we need, because we need to find the theta limits based on this region R, or the shadow R. So that's your shadow R at here. Okay. And then this portion here is region D. Okay. Okay, so now I'm ready to find limits. Okay. So bear in mind, the approach is basically the same thing. Is we're gonna scan through the region D. Okay. How do we scan it then? We're actually scanning in the direction of the coordinates axis. there are three coordinates, rho, phi, theta. So you're scanning in these three directions, step by step. And the first step is to find the rho limits. Scan in the direction of the rho. So let's take a look at together how we can get scan a direction rho. So first, you draw a reading line. Okay. Draw a reading line out of region D. No, sorry, out of origin, right? Out of origin and across region D. Okay, so here's what's happening. So pick, starting from origin, then you draw it all the way across this region D. That's the scan in the direction of the rho axis, right? The rho direction. Okay, so then after this step here, you look for the first contact. Okay, and then you look for the second contact. Okay, so here's your reading line. And the first contact with the region D certainly happening right at the beginning, right? That's the origin. So basically means your rho mean equal to 0. And the second contact will give you the rho max. Okay. Rho max is the location where it hits the top of the surface of the cone, right? Of the region D. And top of the surface is the spherical surface. So in the spherical surface, this is your sphere here. So what do you think the rho value is when you hit the top here? Rho equal to what? Or rho max equal to, from here to here, what's the distance? 1, exactly, right? It's because this is basically rho equal to 1 at here. That's your sphere. So doesn't matter where you draw your reading line here, so your rho max will be 1. Okay. So that's how you get your rho limits. And then the next is to find the phi limits. Okay. So for the phi limits, so let me okay. So phi limits, what you do is, right? If this is the reading line you sketched at the beginning, then the angle phi is the angle between the z-axis and the reading line that you have just sketched. Okay, so the next step is you're going to sweep this reading line. Okay, starting from the z-axis, you sweep all the way across this region D and find the edge. Okay, sandwiching this region D. So apparently, when you start sweeping it, it's already there. So the phi limits should be 0 at the beginning. And then the phi max should be somewhere over here, determined by the cone edge. Okay, so that's how you're going to find the phi limits here. So let me write it down. Okay. So sweep. Sweep this reading line, which is this reading line here. Okay, starting from z-axis across region D. Then you get 2 edges. One will give you phi mean, and one will give you phi max. So in this case, 1 is 0, and the phi max is the angle. Okay, you can draw it over here, or you can draw it over any edge, doesn't matter. So from the z-axis to the edge on the surface of the cone, right, it will be the same. Whether you choose this line or choose this line or choose this line, right, they're all the same phi angle, phi max. And that's given directly by the cone surface. And this is the cone surface, right? Remember what the phi angle is? Pi over 30 degree. So your phi max in this case is 60 degree. Yeah, pi over 3. Did I say 30, right? So 60 degree. Yeah. Okay, so that's your phi limits. And the last step is the theta limits. So theta limits is you have your shadow R over here. Okay. You can draw a reading line out of this region, out of this shadow R at here, and then you can start sweeping from x-axis and then sweep across the real region R and see where the two edges are sandwiched in the region R. But in this case, region R is basically the whole area, circular area in the XY plane. So apparently your theta goes from 0 to 2 pi. Right? So that's your theta limits. Okay. So sweep through shadow R to find theta mean and theta max. So in this case, theta mean is 0 and theta max is 2 pi. So finally, you put everything together, you set up the triple integral. So 1, 2, 3, what are we integrating? We're in dv, so just rho square sine phi, d rho, d phi, d theta. I don't have f of x in this case, but if you do have f of x in some other examples, then you replace all the x, y, z with the corresponding expression for x, y, z. Rho go from 0 to 1. Phi go from 0 to pi over 3. Theta go from 0 to 2 pi. This is a very simple integral, so you can calculate, right? First integrate rho square, and then integrate with respect to phi, and then integrate with respect to theta. So you should get pi over 3, like that. I mean, even if you have a high school, maybe you're still able, you're probably able to calculate this volume using high school, but this is formally through a triple integral calculation. Okay. So as you can see, the technique used here, right, for spherical coordinates is to find its limit is a similar technique as we used to find the Cartesian limits or the cylindrical coordinate limits. It's to scan through the region D. And as you scan through it in your head, you can visualize just like a 3D printer. You're printing through this whole region D to generate this region D, right? Okay. So let me see if we can have another question here. Yeah, I think there's one question probably enough. So let's look at other questions through applications. Okay. Yeah. Any questions on spherical coordinates so far? We're good. All right. Maybe let me show you an exercise, multiple choice here. Let's see if you can get this correct before we move on. Okay. So I need to bring a picture from last year. So here 27. Let's copy the whole thing. Okay, it's a little bit messy, but that's okay. I think you can count. Here's a multiple choice question, basically, right? I'm not sure if you can tell the geometry So the red, okay, the red edges over here give you a geometry of a region D. So you can clearly see the region D has one side, which is more or less, this is actually a cylindrical surface, right? This part here. And then the other part, okay, is that spherical surface. And also the X, Z, Y, Z, and X, Y serving as three sides of this region D. Okay, so basically your region D is given by this, all the red edges over here. So the question is to pick the right choice, essentially to, if you're looking for the volume of this, of the region D, right, what would be the right limits for this region D, okay, for the calculation of this triple integral using spherical coordinates. And this one is a little bit tricky because to find the limits, you will have to somehow use some of the geometric relationships to find the actual limits when you're scanning through this region D. Okay, so I wanted to maybe show it together here just to make sure we understand how it works. Okay, just give me a second, maybe bringing a clear drawing makes Daisy here. Okay, so that's better drawing. Okay, all right. So let's do it together here. Okay, to find the limits, scan through the region D. First, row limits. Okay. So if the row limits, as what we have done, what do we do? Starting from origin, then you create a reading line. Okay, how do I draw this properly? So you draw a reading line out of this origin across the region D. Okay. So apparently your first contact is somewhere on the cylindrical surface, and second contact will be on the spherical surface, right? Okay. So your rho mean is from here to here. Your rho max is from here to here. So I think you can immediately tell me what rho max is. What's rho max? Excellent. Rho max is 8. So that sort of confirms with our finding here, right? Rho max is 8. So what is the rho mean then, right? What is the rho mean? So to find a rho mean, what you have to do is, okay, there are different ways to do this. One way to do this is this. Okay. I'm going to just create an edge over here. And then you can create another edge at the bottom here, which is serve as essentially like an R, right? Okay. Then the way that's generated, okay, it's not very precise drawing. It's like this is your first step of scanning. You're scanning, the first step of scanning is essentially you created this segment of a line at here in a cross section. Okay. So it's not a very precise drawing. Let's see. Let's make it a little better here. Okay. Now, can you see that? Right. So this is your first step of a scanning at here. Okay. And then you're creating this segment of line right here. Okay. So let's focus on this cross section, right? So this cross section here. This is the cross section right here. And your z-axis is somewhere over here. Okay, and this is the origin at here. And the line that we have just drawn is from here to here, right? Yeah. And then this your rho max and this your rho mean. Does that make sense? Yeah. So what is the bottom distance according to the drawing? B, right? You see this circle here, this is a radius, this is a cylindrical inside here. So this is radius of B. So you draw from here to here, still B, okay? Yeah. Then what about the angle from here to here, right? So this is the reading line that we have just sketched. According to the definition, from z-axis to this reading line, what angle do we call this again? Phi angle, okay, good. So this is your phi angle at here. Now, if this is a phi angle from here to here, and then what about this angle here? Right, so let's draw the phi over here, right? This is your phi. If this is phi, yeah, sorry. Exactly, that's also phi, right? Good. So you got phi over here, you got a B over here. So we're looking for, what are we looking for? We're looking for this distance from here to here, which is rho mean. So then your rho mean, what should that be? So technically rho mean, how does rho mean connect to the constant value B from this triangle here? Cosine phi equal to B, right? Triangle here, excellent, right? So you're looking for rho mean, so rho mean equal to B over cosine phi. That makes sense? So that's, you can see here, this is B over cosine phi, right? So I guess you can already actually make a choice because the other two obviously not right. So this is your, the third, sorry, did I, what did I say here? Rho sine, right? What do I say? Rho sine phi. Right, rho sine phi at here. So your choice is actually already gone. It's the second choice over here, right? Yeah. But of course, the next thing you had to be able to tell is, how did you find that phi limits? You see the phi limits for this one here? I don't have time to do this anymore, but I can finish this probably in the next lecture. How do we find the phi limits, right? So the phi limits, according to the, so you need to find from this edge to this edge. So this edge is easy, pi over 2. So it's the angle corresponding to this edge give you the phi mean, okay? Yeah. And that's also kind of, you basically make use of, again, make use of the geometry to find this phi mean. So I'll finish this in the next lecture. Okay? And then we have a application of a triple integral to do before we move on to the next new topic, okay? Yeah. All right, so any questions, feel free to come over here. Okay, otherwise, have a good night.